lecture of this week, we derived the governing differential equation of buckling by substituting the expression of the torque per small length dz by considering a cruciform section. Further, we found the critical load for torsional buckling for a cruciform section. And finally, we took a case to solve the governing differential equation of buckling to find the critical load of torsional buckling for a column when ends of the column cannot rotate and are free to warp. Now, we will take another case to solve the governing differential equation of buckling to find the critical load of torsional buckling for a column when both the ends of the column are rigidly built. Take an example. The boundary conditions are given like this. Both ends of the bar are rigidly built and cannot warp, that is completely restrained. For this condition, we will find the expression of the critical load for torsional buckling. First of all, we will have to write the general solution of this governing differential equation. Then we will use the boundary conditions to find the constants in the general solution. Let me first write down the governing differential equation for torsional buckling, that is d to the power 4th phi by dz to the power 4th plus p square into d square phi by dz square is equal to 0. This is the governing differential equation, and the general solution is phi is equal to a1 sin pz plus a2 cos pz plus a3z plus a4. And the boundary conditions, both ends of the bar are rigidly built. Then we can write here, this rigidly built means this phi is equal to 0 at z is equal to 0 and z is equal to L. And we can write another boundary condition, that is d phi by dz is equal to 0 at z is equal to 0 and z is equal to L. Generally in the fixed beam, there is slope is equal to 0 as well as the displacement is equal to 0. Similarly, if the column is restrained, then it is not allowed to rotate. If we will substitute this, let us will first use the condition phi is equal to 0 at z is equal to 0, and we will get the first equation. That equation 1 you can get if you substitute phi is equal to 0 at z is equal to 0. If you substitute in this equation in general solution, what it will be, that phi is equal to 0 means 0 is equal to a1 into sine value, that will be coming 0, plus a2 cos value, that will be coming 1, plus a3 z is equal to 0. So, that is, you can write 0 here, plus a4. So, this is the first equation we got from the given boundary condition. The second one is phi is equal to 0 at z is equal to L. Similarly, if we substitute in general equation, we will get 0 is equal to, this is a1, then sin PL plus a2, that is cos PL, plus a3 into L plus a4. So this is the second equation we got by using the given boundary condition. Then this is equation 2, here you can write equation 2. And if we use next boundary condition to get equation 3, here is d phi by dz is equal to 0 at z is equal to 0. How to do? You will have to differentiate this. Then if you will differentiate, then phi that will be 0 equal to 0. Then if you will differentiate, that will be this one sine. If you will differentiate, it will be cos, and the coefficient will be a1 with a1. That p will come, because once we are differentiating sin pz with respect to z, so automatically p will come. Here you can write a1 into p, and cos value that will be 1. So because of that, it is alright a1 into p plus a2, and here this is cos. If once you will differentiate, it will sin. If you will substitute z is equal to 0, automatically it will become 0 plus a3. If it is differentiated, that will be simply a3. So a3 into 1 you can write here, and plus the constant, if you will differentiate, that will become 0. So this is the third equation we got. And the fourth equation is, this is d phi by dz is equal to 0 at z is equal to L. So if you substitute at z is equal to L, 0 is equal to, it will be, if you will differentiate, that will become a1p. Sin, if you will differentiate, it will become cos pl, and there is cos, and if you will differentiate, it will be minus. So you can write minus a2p into sin pl. Then plus, if you will differentiate, that will be a3, then next it will be 0. So this is the fourth equation. If we will write the all four equations together in matrix form like this, and for non-trivial solution, this coefficient matrix is to be 0. So the characteristic equation will be the determinant of this coefficient matrix, and if you write it, this is the characteristic equation, this is equal to 0. If we expand it, it will become 2 cos pl minus 1 plus pl sin pl is equal to 0. Implies, if we write sin pl by 2, then it become pl by 2 cos pl by 2 minus sin pl by 2 is equal to 0. This implies as sin pl is by 2 is equal to 0, or pl by 2 cos pl by 2 minus sin pl by 2 is equal to 0. If this is the condition, then we can write pl by 2 is equal to n pi, which implies pl is equal to 2n pi, and for n is equal to 1, this p becomes 2 pi by L. And if we will write the expression of p square, that is for torsional buckling, that expression of p square we had derived as sigma cr I naught minus c divided by c1, and if we substitute this expression, this become p square is equal to 2 pi by L whole square. So that you can write here 2 pi by L whole square is equal to sigma cr I naught minus c divided by c1. And if you simplify further, this sigma cr is equal to 1 by I naught multiplied by c plus 4 pi square by L square into C1. This is the expression for sigma CR. Let us will go for the other solution. The another solution of characteristic equation, this is the thing. And from this we will get 10 PL by 2, that is equal to PL by 2. And we will have to solve this transcendental equation, and the solution is PL by 2 is equal to 4.4928. And once we got this, if you substitute the P value in the expression, P square is equal to sigma CR I naught minus C divided by C1, then the expression of this sigma CR, the critical stress value is 1 by I naught into C plus 80.75 L square into C1. Here you see I directly wrote the root of this equation, and this can be easily solved graphically. Then I have plotted solution of this equation, and here you see this is the solution of this transcendental equation. The transcendental equation is 10 PL by 2 is equal to PL by 2, and the first equation is y is equal to PL by 2. This is one equation, and another equation is y is equal to 10 PL by 2. These curves are 10 PL by 2 and this is PL by 2. And this is, here you can write this is PL. This is all small l, yes. Here the intersection of these two curves, y is equal to PL by 2 and y is equal to 10 PL by 2, they intersect at this point, and the smallest root is 4.493. So this is the solution of this equation. This is the minimum root of this equation is 4.493, and from that we substituted the value of P square and we got this expression of sigma CR. Let us analyze these two results. One is sigma CR is equal to 1 by I naught C plus 4 pi square by L square C1, another is 1 by I naught C plus 80.75 L square into C1, and this is the antisymmetric mode of buckling. This is antisymmetric mode of buckling, and when the mode is antisymmetric mode, that time the critical load is this 1 by I naught multiplied by C plus 80.75 divided by L square into C1. And if it is symmetric mode, and this is the critical load, sigma CR is equal to 1 by I naught multiplied by C plus 4 pi square by L square into C1. And this we solved. Next what we will do, next objective is to derive the governing differential equation of torsional flexural buckling. Let us discuss torsional flexural buckling. Generally, for open column section or unsymmetrical column section, when load does not pass through the shear center, the column undergo torsional flexural buckling. We had already derived the governing differential equation for non-uniform torsion, means that was the governing differential equation of torsion which involves both uniform torsion as well as non-uniform torsion. If you see this figure, this C is the centroid and O is the shear center. When the section is subjected to axial load, the section undergoes translation as well as rotation. This centered C moves to C double dash and the shear center O moves to O dash, and Cx and Cy are principal centroidal axis, and O is the shear center and C is the centroid. And during translation of the cross section, point O moves to O dash and this C moves to C dash, and during rotation this C dash moves to C double dash. This is due to translation and this is due to rotation. And finally, the coordinate of C double dash is U plus Y naught phi and V minus X naught phi. Here this U and this V, they are due to translation, and this Y naught phi and this X naught phi, they are because of rotation. If you see this figure, the centroid C moves to C dash, that is translation movement. You see, C to C dash, this distance is U, and if you see the other distance, this is Y coordinate, this is V, and the shear center also, the translation movement also same, that is O moves to O dash, this also same, this is U, and this also same V. So the translation of centroid is same as the translation of the shear center. And if you see the distance of the centroid C to shear center, this was Y naught and this was X naught. This was the initial distance, that is from centroid to shear center. This distance also remains same after the translation movement. You see, that is O dash to C dash, this distance is same. This is X naught and this is same Y naught. Now in rotation, the C dash moves to C double dash. Because of that, there is the change in coordinates. Let us look to that. Coordinate of C dash becomes U plus Y naught phi minus V minus X naught phi. Let us X coordinate of C double dash, we can write as U plus X naught. I mean this is U and this is X naught. Then we will have to subtract this distance. We will have to subtract this distance. So that will be minus O dash C double dash cos phi plus alpha. If we will expand cos phi plus alpha, that becomes U plus X naught minus O dash C double dash cos phi plus alpha, so is equal to U plus X naught minus O dash C double dash cos phi into cos alpha plus O dash C double dash sin phi into sin alpha. So this cos phi, as phi is very small, that is equal to 1, and this sin phi value is equal to phi. Finally, it will be reduced to U plus X naught minus X naught plus phi into Y naught. So it will be U plus Y naught phi. So this is the X coordinate of C dash. Similarly, we can derive the Y coordinate of C double dash is equal to V minus X naught phi. So we got the coordinate of C dash, that is U plus Y naught phi, and v minus x naught phi. Hence, we can write the bending moment with respect to principal centroidal axis as like this. So, let me write bending moment about x axis, that is mx, that is minus p into v minus x naught phi, and this is the y coordinate, and bending moment about y axis, that is my, is minus p into u plus y naught phi, and this is x coordinate. So, this can be written as EIXX into d square v by dz square is equal to minus p into v minus x naught phi, and this equation can be written as EIYY d square u by dz square is equal to minus p into u plus y naught phi, and these two are governing differential equation for bending about principal centroidal axis. If you see here, this small strip ds into t, because of the application of the load, the section got deformed, and this small strip, the translation component of small strip, that is small strip is ds into t, is same as translation component of centroid. However, the rotation of the considered strip about the shear center will be less than that of rotation of centroid about the shear center. Hence, inner x coordinate of the strip will be u plus y naught minus y phi and v minus x naught minus x phi. This section is in between centroid and shear center, and the section is undergoing rotation about shear center. So, the shear center coordinate is x naught y naught and the strip coordinate is x and y. So, definitely final coordinate of the strip is u plus y naught y phi and v minus x naught minus x phi. This uv is the translation component. This is, you can write here, translation component, and this is due to rotation. If a column is subjected to axial load and if there is transverse displacement v at a distance, let it is at distance z, then we write the governing differential equation as EI d to the power 4th v by dz to the power 4th plus p into d square v by dz square is equal to q. And if q is equal to 0, then simply we write EI d to the power 4th v by dz to the power 4th plus p into d square v by dz square is equal to 0. So, in this case, the column is subjected to only the axial load. We can also write this equation as EI d to the power 4th v by dz to the power 4th is equal to minus p into d square v by dz square. In this case, the column is having transverse displacement of v and it is subjected to load p, okay, and We can also make it equivalent column with fictitious lateral load of minus P into d square V by dz square. I can consider this column is having no axial load, and that column is subjected to a fictitious lateral load of minus P into d square V by dz square. Similarly, in this case, the x coordinate of the strip is u plus y naught v into phi and v minus x naught minus x into phi. So, we can also write the column is subjected to the fictitious lateral load of intensity P into d square V by dz square. In our present discussion, the final x coordinate of the strip is this and final y coordinate of the strip is this. This is the final y coordinate. This is the final y coordinate of the strip. And by seeing this x coordinate and y coordinate, we can write the fictitious lateral load of intensity minus sigma into T into ds multiplied by P into d square u plus y naught minus y into phi divided by dz square. This is the fictitious lateral load of intensity this much. This is because of x direction displacement. This thing is x direction displacement. And fictitious lateral load of intensity because of y direction displacement. Let me write fictitious lateral load of intensity, that is minus sigma t into ds into d square by dz square into v minus x naught minus x into phi, and this is y direction displacement. And we got the fictitious lateral load in x direction as well as in y direction. And if you see this open section, this strip is subjected to the lateral load of some intensity which we derived. This much is the intensity of load in the x direction, and this much is the intensity of load in the y direction. This is acting on this small strip ds into t. So, that fictitious load, what it will do? It will try to rotate about the shear center, and if you see this, if in x direction, if the load is acting like this, that will try to rotate about the shear center. It will be a clockwise moment, and in y direction, if there will be fictitious lateral load, if that will be acting like this, that will give a anti-clockwise rotation. So, one will be positive and other will be negative. Let us consider this clockwise is positive and anti-clockwise is negative. Then we can write the final expression of this net moment about this shear center, that will be like this. That is, let me write down here, taking the moment about shear center of above fictitious force, taking the moment about shear center of above fictitious force for unit length in the longitudinal direction, that becomes dmz, that becomes minus sigma t into ds multiplied by y naught minus y, and this multiplied by d square u by dz square plus y naught minus y into d square phi by dz square plus sigma t into ds multiplied by x naught minus x into d square v by dz square plus x naught minus x into d square phi by dz square. Yes. Here we have multiplied this y naught minus y to the fictitious force and x naught minus x to the fictitious force. Here you see this, the force in the x direction, that will be multiplied with this distance. So, this distance is y naught minus y, and this force in the direction of y, that is to be multiplied with this. So, this value is x naught minus x. So, that has been multiplied here. So, we got the moment about the shear center by both the fictitious force, and if we simplify this, this will become mz is equal to, you will have to integrate in total cross section of this section. So, total cross section means you will have to multiply it with complete area A, and this is dmz. If you will integrate it, that will become P into x naught multiplied by d square v by dz square minus y naught into d square u by dz square minus ixx plus iyy plus a into x naught square plus y naught square multiplied by p by a into d square phi by dz square. Here this is I naught. Here what we have done, we have substituted sigma into integration t into ds is equal to p. First is this. Second one we have substituted as y square into t into ds, that is ixx, and third we have taken x square into t into ds is equal to iyy, and fourth one we have considered x into t into ds integration, this equal to integration y t into ds equal to, this is area, integrating throughout area, and this equal to 0. This we got because of CG, because CG at 0, 0. And if you substitute this thing 1, 2, 3, 4 condition in this expression, then we got the expression of mz is this much. This expression of the mz is the torque per unit length in the governing differential equation for non-uniform torsion. Means we had derived the governing differential equation for torsion which includes both uniform torsion as well as non-uniform torsion. That expression we had derived, if you remember, that expression was C1 d to the power 4th phi by dz to the power 4th minus C into d square phi by dz square is equal to m. In this governing differential equation, this involves both uniform torsion as well as non-uniform torsion. So, now we derive the expression of this mz. Now, if we substitute this expression of mz here, the expression of mz we derived this one. If we substitute this in this governing differential equation what we had derived earlier, that will become C1 d to the power 4th phi by dz to the power 4th minus C minus I naught by A into P into d square phi by dz square minus P into x naught d square V by dz square plus P into y naught d square U by dz square is equal to 0. So, this is the governing differential equation corresponding to rotation about shear center. And if this equation is C, and two equations we had derived, that was bending about principal centroidal axis, that let me show you again. Yes, this was two governing differential equation bending about principal centroidal axis. If this is A equation and this is B, and this is the final expression we got, this is the C. This A, B, C equation, A, B and C are three coupled governing differential equation for buckling by both bending and torsion. These three equations can be used to determine the critical load. Thank you.